Things. No, in retrospect, I should have done today's lecture last Thursday and Thursday's lecture today because you're already kind of dealing with classes and header and source material stuff. The thing of today's lecture um, in the lab, but you also still have a good week to go on the lab. So what I am going to do is illustrate all the concepts from today by actually going through the lab. And I understand the TAs went through some of the stuff, so some of it may be repetition, but most of it I think is going to be new. The class notes for today go over a tic-tac-toe game. And if you're looking after the lecture today for some more examples of using multiple files for a program, look at that. And I had a good question at the beginning. It was kind of how to balance the zyBooks with the lecture notes. And the way I look at it is the zyBooks are giving you the detailed technical information, and the lecture notes tend to flesh that out with a big example. Dr. Plank likes to use examples from his research or from his personal life, as you probably have already seen, to flesh out something as a kind of big real-world example. It can be a little harder to find the nuggets in Dr. Plank's notes, although he now tries to summarize the big points at the end of his notes. So for example, today, if you go to the end of his notes for the tic-tac-toe, you will find him summarizing the main points of the lecture. So he tries to bring things together at the end. So again, the Zyanti or zyBooks, very good for the essential technical material we're covering, but it's, tends to be short and punchy. It doesn't really get into big examples. Dr. Plank's notes, much more expansive and tend to get into fairly big examples. Okay, second thing, I have found that Mingal 217 is a little too busy and crowded for my office hours. I found a more secluded place. So my office hours will now be held on the landing on the second floor near the stairwell. That's the main stairwell. And there's a couple tables there. I found that it's quiet, a little easier to conduct office hours. Also today, I have to take off early, so I'm going to start my office hours a little earlier at 3:15. I might even be there as early as 3. And I am going to have to take off around 4:05 today. So that's just for today. That's what the office hours look like. Okay. So the topic of the day is several things, as the notes say. So we have classes. We also have this notion of, we have classes, and we also have this notion of multiple files that we are compiling. So you have already seen the basic things with classes. So I'm actually going to go to the lab right now. Just walk us through an example there. So with a class, we have what are called methods, which are functions inside the class that can be called, and we have member data. Typically, we protect our member data so that it is not visible to the rest of the world. And that allows us to easily change our implementation. A classic example of that is when we get to linked lists in a couple weeks. There's multiple ways to do them. One is with vectors, one is with lists. and you'd like to be able to easily change the implementation from a vector to a list or a list to a vector without breaking people's code. Another example here is if we decided that we were going to change from using a vector to a straight 2D array, and the member data was public, meaning that programs could access our pixels vector, now all of a sudden all that code would break because it was engineered to work with a vector and not an array. So when we protect, the reason we protect member data, write it down, the reason we protect member data is to make it easy to change the implementation without breaking the programs that use it. So the reason to make the data protected in a class is so that we can easily change the implementation without changing or without breaking the programs that use this class.
We can't see about this.
Too much zoom. Okay, thank you. Is it still easy to read this in the back? It's still, okay. So, in general, we say that the data, or the implementation, is unstable, potentially unstable. And therefore, we want to hide it. Whereas the API, the Application Programmer Interface, is stable. We try not to change it. Okay, and the API is the public methods. So it's the way that you're able to manipulate the state information in an object. Okay, so the API is stable. We can count on it not to change. Therefore, programs that use the API, they're never going to be broken. Whereas the underlying implementation, potentially unstable, subject to change, but because we're basically making the object a black box and not showing how the sausage is made, so to speak, it's not a problem, okay? And I know that there are two different keywords you can use to protect your data. One is private and one is protected. What we want you to use is protected. And for some reason, there we go. Okay, so we prefer that you use protected rather than private. Okay, there's typically two types of methods. One we would call accessor methods that allow us to access information. We don't really have any accessor methods here. The other is mutators. So we have accessor methods and mutator methods. Accessor methods allow us to access information in the object. If we had a method for accessing individual pixels in this vector, that would be an accessor method. Mutator methods change the state of the object, and all of these methods that you're using in the lab change the state of the object. For example, the read method reads a new PGM file into your pixels vector. The clockwise method rotates it by 90 degrees. So all of them change the state of your object somehow, and we call these methods mutator methods. Now, you notice this const keyword at the end of the write method. That indicates that that particular method will not change the state of the object. It's a promise to the compiler that we will not change the state of the object. In this case, the only state information is pixels, so we're guaranteeing that the write method will not modify the pixels array. None of the other methods make this promise because, in fact, all of the other methods change the pixels array. Normally, your accessor methods will be declared as const because your accessor methods typically don't modify the state information. Instead, they simply return information about the object. So normally, your const methods will be accessor methods. Okay, this write method is a little bit unusual. It's writing to a file. So it's changing some state information, but in this case, it is on a file system. So it's neither really an accessor method, nor is it, in the strict technical sense of the word, a mutator method. But we would classify it as a mutator method because it's modifying state information somewhere, in this case on a disk. Okay, so const, when put at the end of a method declaration, indicates we are not going to modify the state information. Now, we typically separate the declaration of a class from its implementation. So this part goes in what is called a .hpp file. Okay, you may have heard of .h files probably in 130. Yes, you use .h files, maybe, maybe not. No? Okay. So you did not. Okay, so these are called header files. They contain class declarations, function prototypes, but not their implementation, not C++ source code. Those go in a separate .cpp file. Okay. So that is where Dr. Planck then started to say, okay, we are going to have separate directories, and he has a source directory. He had, whoops, if I could spell correctly, a source. He has an include. He has a bin. And he has an obj. I think on top of that he has a PGM, but that's a bit different for this project. So for many projects done in C++, or actually in a compiled language like Java, C, you'll have 4 separate directories like this to partition your files. So your source directories contain the .cpp files. The include directories contain your .hpp or header files. Your obj directories contain your .o files, and your bin files contain your executables. Okay, your executables is what you are eventually hoping to get to. The general idea is that you have your source and your include directories that are going together, and they are compiled into .os, which go into the obj directory, and then a linker takes your .o files, compiles them into executables, which go into the bin directory. Okay, so the source is going to often contain multiple .cpp files. In the case of your lab 3, it contains 2. One is your Pgm file. So in the lab, the source contains pgm.cpp. And I believe he calls it Pgm tester. Okay, these 2 files are going to get compiled into the eventual Pgm tester program. Okay. And I'm going to make sure that I'm not confusing you by using the wrong. I think he's using, yep, Pgm tester. Okay. So we're going to have 2 files. They're going to get compiled into .o files. And we can use a process that is called separate compilation to do that. Separate compilation is where we separately compile each of the files. Okay, we can do that with the C command or C flag. So if we say G++ C, it will create a .o file. Okay, and we need, in this case, to tell it to put where to get it, where to put it, where the include files are, so on and so forth. And so rather than writing it here, I'm going to switch back and actually look at the makefile. Come on, what is going wrong? That's what was going wrong. Okay. Okay, for a moment, don't worry too much about what you're seeing. I'll explain the make files in a moment. What I want you to look at right here is this G++ statement. So we are using the -c flag to specify that we're just going to output a object file. The -o flag indicates where that file is to be placed and how it's to be named. So we're going to put it in the obj directory and name it pgm.o. We are going to be compiling from the source directory and compiling the program pgm.cpp. Now this assumes that we are compiling from the parent directory. If you were compiling in the pgm.cpp directory, this command wouldn't work because it would try to find the source directory and would fail. So we're assuming that we are compiling from the parent directory here, the one that contains source, obj, bin, etc. Now you see the C flags here. This is introducing, this is a macro variable, and it is taking what's being substituted down here for $C flags is this right here. So this std equals C++98. We want all compiler warnings, so -W is some directives to the compiler about warnings, and we want even extra compiler warnings to make sure that we're not doing anything funny. And then this is a, whoops, big statement right here. This -I include, the -I says if you're looking for header files and you can't find the ones you're looking for, look in this include directory. Okay? So if you have, normally thus far you've seen all header files in these inequality braces, right? When they're in inequality braces, when you see an include statement, let's go back here for a moment. When you see an include statement like this, it is a system file. Okay, and the compiler knows where to look for system files. But if you look at pgm.cpp, you will see this, program include quotes, pgm.hpp. Header files in quotes are programmer-defined header files. And the compiler doesn't know where to find them. By default, it looks in the current directory. But you don't always have your .hpp files in the current directory, as in this lab and in all your remaining labs, the header files will be in an include directory. So you need to tell the compiler where to find your include files, and you do that with the -I flag. You can have multiple -I flags if you have multiple include directories, and on large projects you would have multiple include directories. Here we just have the one. Also, if you're wondering when you type make why you can't seem to use your 4 range loops for vectors, the reason is right here. You can see that Dr. Planck is compiling with the C++98 flag. So you would need to change that to be what? C++11 if you want your programs to be able to use some of the C11 standard stuff. Okay? So because he doesn't want to repeat this all the time, make gives us a way of putting all this information in what's called a macro, which is C flags. And so down here, when we say $C flags gets replaced by this stuff up here. Okay? So what we are doing is separately compiling each of our files. Okay, and you might wonder, what is the advantage to separate compilation?
Change one file, it only compiles the one.
Very good. If you change one file, you only recompile what you changed. But yeah, we'll get to that. You can't avoid that. But there's no sense recompiling files you haven't changed. It's not such a big deal in 140 where you may only have a couple files, but imagine being on a big project with hundreds of files and you change one. It really makes no sense to recompile the 200 files you didn't change. Okay, so that's why we talk about separate compilation and only wanting to recompile those files we actually changed. Just a moment.
It's an example of what we were talking about. In
Okay.
high school robotics, Eclipse doesn't do separate compilation.
Mm-hmm.
So when we would change one command file for the robot, it would recompile all 300 other files because
Wow.
we had like 72 different commands and then all the different subsystems and all of that. And
Okay.
that includes
And how long did that take?
3-4 minutes.
3 to 4 minutes per change. So there you have it. He was
And
just.
It was changing one number, so
Mm-hmm.
backspace changes 0 to 1.
And now you have to recompile and wait for
And then
3
you
to 4
have to
minutes.
reload it to the robot, and
Mm-hmm.
it's like a 30-minute long process.
Right, just to change one number. So that's a great example of why you want to do separate compilation. Okay? So in this case, our program has two files, so there are two commands for doing compilation. I'll get to, again, explanation of the make file in a little bit. But you can see here there are two commands, each that compiles one of the two files. Then we have a command to compile the executable, and really it's not compiling. Even though we're calling G++, we're actually invoking the linker here. Okay, so you see again we name our output file bin pgm tester, and we are linking in these two .o files. Okay, so we're invoking the linker, and it is linking together these two files to create an executable. Okay, so what is the linker doing? Let's have a look. So if we look at Dr. Planck's code, we will see that he calls some of your functions. So here he has pgm.read. Well, this read function is not defined in this file. It's defined in the pgm.cpp file. So when the compiler compiles the pgm tester file and creates a .o file, what it does is it outputs some code, and if there were globals, it would output some area for the globals. But what it's also putting out is, I'm going to call it a link table, or a, I'm going to call it functions defined, and then a separate table for functions not defined. So in his pgm tester, he has main defined, but he has a whole bunch of undefined methods. In fact, I should have made this one much bigger. So undefined are pgm : read, pgm : write, pgm : create, plus all the other methods that he calls. Okay, so we're putting out code segment, a functions defined table, and a functions not defined table. Same thing in our, sorry, this was pgm tester, not pgm.o. In the pgm.o, same thing happens. It puts out code. It puts out functions defined. Okay, and it has pgm write, pgm read, pgm create, and functions not defined is not actually calling any functions that it doesn't already know about or that aren't system defined, so this table would be empty. Now, when the linker puts these two programs together, what it does is it combines the two code segments. So I'll call this code 1 and code 2. So it combines the two code segments, and it resolves the undefined functions. So the linker tasks combine code segments from different .o files. resolve undefined functions using the functions defined table. So everywhere in this code, so up here in this code 1, there are places where it's doing a call, but it doesn't know where it's calling to, because it's really going to be calling into code 2. So when the compiler compiled pgmtester.o, it put in some stubs for, say, pgm read. So I'll call it a read stub, a placeholder. Now it is going to go through, and this function's not defined. It's also going to have the addresses. So it's going to have addresses of calls to read. So the linker is going to go through this list of addresses, and it's going to, well, first of all, it's going to search the functions defined table for all .o files looking for pgm read. When it finds it, it's now able to figure out what its address is. Somewhere down here, there is a read function defined in code 2. It knows its address, and so the linker will replace whatever this address is, say 0x1000. It can replace it in effect with 0x1000. Okay, not quite that direct, as you know from the assembly language, but a close enough approximation. Okay, so again, down here, this program read would have an address. Maybe it was 0x, say, 400. And you're saying, okay, why is it 0x1000 here and 0x400 here? Okay, the reason is that code 1 perhaps goes from, say, 0 to, we'll say, 600. So now read gets displaced down to 0x1000. So the linker also has to adjust addresses. Okay, and adjust addresses based on where functions actually are placed. And you can't read that. Okay, so the big job, we call it a linker because it is linking the functions, the undefined functions, with the functions that have been defined in other files. Okay, also at this point, this is why you sometimes get multiply defined functions. When you bring this all together, the linker may find multiple instances of program : read. If there's more than 2 .o files like there were here, the possibility exists that there were multiple pgm : reads, and in that case the linker will give you an error message saying there's multiple instances. Now it's okay if we are using polymorphism, but if we have 2 pgm reads with exactly the same prototype, this is where the linker will squawk. Okay, and you get those LD errors. So when you see LD colon, those are your linker errors. Okay, so questions about what the linker is doing. Clear enough? You could, if you were asked on a test to parrot this back to me, you could. Okay. Okay, so what I want to talk about next is this makefile. What is happening in this makefile? Makefiles are a program in Unix that makes it easy to manage projects like your labs. So the idea is that you're able to define what are called command names. Clean, this is a command name, this is a command name, and then the command deals with some files. So you have the command name, then a colon, then the files that this command deals with. So in this case, pgmtester.o, it's dealing with pgmtester.cpp and include pgm.hpp. Then on a separate line with a tab, you have the command that's actually getting executed. Okay, in this case, it's G++, it's compiling into a .o file. Okay, now, the reason that you provide a list of files associated with the command is that make does a very nice service for you, which is it will execute, it will check to see whether those files have been modified since the last time we executed the command. And you may ask, okay, how do I know whether pgmtester.cpp has been modified since the last time I executed this command? Anyone have an idea?
It's that file.
You can look at the file and it gives the times at which they were compiled.
You check the destination of the source. See if it's
So the way I typically do it is, in this case, I look at the source. And you can see that PGM tester was compiled yesterday at 1528. If I do an L on the PGM tester, you can see it was compiled at 1531. Therefore, it hasn't changed. PGM tester.cpp has not changed since the last time I did PGM tester. Okay, so if I typed at this point, make source pgm tester actually it's obj, sorry. Make obj pgm tester.o, it says it's up to date. Okay, because when it looks at the timestamps for the two files involved in the command, they predate the timestamp on pgm tester.o. Now, let's say I touch. This is just going to make it look like I changed the source code. Okay, and if I do an ls on source, we can now see it looks like I have modified the file. Now if I do a make, you see it executed the command because it no longer, when it looked at the timestamps, it saw that the timestamp on pgmtester.cpp was more recent than the timestamp on pgmtester.o, and therefore the command needed to be rerun. Now you may ask, how did it know to look at pgmtester.o? And the reason is that's the name of the command. So you actually, with make, give the command name is typically the name of the file that you wish to create. So in this case, the name of the file I wish to create is in the obj directory with the name pgmtester.o. There are a few, you don't always have to name your commands with the file name, but if you do, that's the file that will be, whose timestamp will be checked to see if the command should be run. So make clean is always run because there is no file called clean. So it is run unconditionally because there's no timestamp associated with it. But if the command name is the name of a file, it will check the timestamp on that file and only run the command if the timestamp on the command file is less recent than the timestamp on one of the source files. So these are called source files. This is the dependent file. And this is the command. So in general, with a make, it is a command name, a colon, then the source files, separated by spaces, then a command with, I will put T because you use a tab, and then the command. Okay, the command name is often a file name whose timestamp is checked before the make command is executed. Okay, and the make command is only executed if the timestamp on one of the source files is more recent than the timestamp on the dependent file, i.e. the file in the command name. Okay? So that's what you're looking at when Dr. Planck creates a makefile. A makefile is a sequence of commands that are labeled with command names. So when you type make, you typically give it a command name, and it executes that command name. If you don't give it a command name, then it goes to the top of the file, and you see here it says all equals. So if you just say make without anything else, in this case it's going to execute the all command. Okay, now the all command only executes one command, which is bin pgm tester. But if your files are changed, pgm tester will go back. What is going on here? Okay, so pgm tester will first check to see what are the timestamps on the .o files. Okay, and it will then go back to the .o files to see whether anything needs to be updated with the .o files, whether those timestamps. So there's kind of like if you want to think of it, a dependency graph. So we say that pgm tester depends on pgm.o.
We can't see the projector.
Oh, thank you. So it depends on pgm.o and pgm-tester.o. These in turn depend on pgm.cpp and pgm.hpp. So when make goes to execute this command, it first goes and looks at whether it needs to remake those two files. And in checking that, it then sees for pgm.o, it needs to check the timestamps on these two files. So make actually kind of follows this dependency chain for you to make sure that everything is up to date before you execute the command to make pgm tester. So that's why you're always listing your source files so that make can ensure that it compiles or executes those commands that are necessary to bring everything up to date. Now, you're not going to have to write make files in this course, but I do want you to understand roughly their structure. Okay, if I were to ask you on a test roughly what the structure is or what they do, I expect you to be able to do that. Okay, so the big thing is command name, colon, source files, then a command that gets executed. The command only gets executed if the timestamp on a source file is more recent than the timestamp on the command file. If it is a command that it does not map to a file name, the command is executed unconditionally. And you can see here, clean does not depend on any files. The command still appears on a separate line. Okay? And you can see here, the clean command calls remove F on your object and your bin directories, just cleaning out those two directories. Okay? So questions about makefiles. We good? Okay. What else do I need to say before I dive into the tester program? Okay. One thing about the naming conventions. So you'll notice that when we named our include file pgm.hpp. Okay? And the class was named pgm. You name the .cpp file the same name. Now normally you would have capitalized the P, so in the source file, but the general naming convention is that the name of a class determines the name of its .hpp and .cpp files. Namely, you use the same name. Whatever name you use for the class, you use the same name for the .hpp and .cpp files. Makes things easy, especially when you get out in the real world and you use IDEs, integrated development environments. They typically use these standard naming conventions, so they find it easy to find where things are stored.
Just IDEs, if you're working in C++, and you go to create a class, will just make it all for you.
Yes, so in fact, the IDEs will make all that stuff for you automatically. You won't even have to do it. Once you start a class PGM, it will create the .cpp and .hpp files for you. Okay, now, you can also define classes that use other classes. So, in this case, let's say that we want it. So, most pixel files actually aren't as simple as grayscale. Let's say that we used instead what is called the RGB model. So in the color models, if these PGMs that you're getting are grayscale, okay, they're black and white. And the 0 to 255 is the intensity of the grayness going from white to black. But when you're using colors, you often use three values called red, green, and blue, RGB, to indicate the color you want created. And there, the color intensities also go from 0 to 255, but it defines the intensity, or in this case, the amount of saturation of the color. So I always forget, but I believe values closer to 0 mean more white, values closer to 255 mean more pure. Okay? So, in that case, we couldn't use a single integer to represent our pixels. We would have to have instead a way to represent an object that had 3 values. So we might define another class, in this case called pixel, and in this case it would be a class that doesn't need to be seen necessarily outside the outside this .hpp file, but nonetheless we kind of have to have it. So we make it protected, int red, int blue, int green. Some public methods such as a constructor function that would create. We haven't really talked about constructor functions yet, but this one would create initialize the values to RB, and G. We might have some functions, accessor functions to get. And some setter functions. Okay, so this would be a simple class to store a pixel that has 3 integer values. And now down here we could say, instead of that is a 2D vector of ints, we could say that it is a 2D vector of pixels. Okay, so we can have vectors that store objects. And clearly, in this case, we can have classes that store objects. In this case, a PGM class would be storing a 2D vector of pixels. Okay, so it's okay to use classes inside other classes, like this. So questions about that? Okay. Now, final thing for today is that we want you to develop programs incrementally, and we would like you to test your programs. So Dr. Plank always writes a tester program, and I always see questions on Piazza that show a lack of understanding of what his tester program is doing. So first of all, he writes these tester programs so that you can develop incrementally. In this case, he has written a PGM tester program that reads commands from standard in and executes those commands by calling them on your methods that you've defined. And you can see he's essentially defined commands for every one of the methods you have, plus a Q for a quick, plus a question mark that prints commands in case you forget what they are. Okay? So this facilitates writing your programs incrementally. The first thing he suggests you do is you write the read method. You don't have to write any other method. You can just put stubs in. Okay, you can see that I did that for mine. I put in stubs for all the other programs. They just have them returning true right now. Okay, and he gave you the read function, so it turns out you don't have to write read because he provided it for you. But if you had to write the read function, that would be the first one you would write. Then he actually suggests you write the write command next, because at any time you do anything with a PGM file, you essentially have to write it out. So all your other commands essentially rely on this write command. So that would be the next one that you write. And then probably create would be the next one, just so you could create a simple PGM, and then you'd start writing your other ones. But the point is, by writing this tester program, he's given you a way to write your functions one at a time rather than all at once. Okay? And that's the way we want you to develop your programs incrementally, because it's a lot easier to debug one function at a time than it is trying to find a bug in multiple functions. Let's say you write all of your functions and then you write CCW, and PGM tester maybe tries to write it out. Well, it bombs, there's an error, and you're left wondering, was the problem in CCW or was it in write? Well, if you had first written your write command and thoroughly tested it, you would be pretty confident the bug was in CCW, thus reducing your debug time. Okay, the less code you have to look at, the faster you'll find the bug. Okay, it's just a fundamental thing of search and rescue. The smaller the search area, the better your chance of finding something fast. Same thing with programming. Why we want you to do it incrementally. The less code you have to look at, the faster you find the bug. Okay? So, he's written this tester program, which he pretty much gives you for all the labs. But it can't hurt for you to know how it's done, because in the real world, you might have to write your own testing framework. In fact, you will have to write your own testing framework. Okay, so let's just take a look at what he's doing with his tester program. What you can see is it takes these commands, reads them from standard in. So he's going to need to read a line at a time. The first word tells him what the command is. So essentially, he's just writing a big if-then-else program. He's going to read lines one at a time, look at the first word. Based on that first word, he's going to determine what command he's executing. Okay, so what he does, he has his print commands, which I'm not really going to worry about. He has a vector where he's going to break his line. He's going to read a line. He's going to break that line into a vector of words, which he calls SV for string vector. So he's going to break each line into a vector of words, and he's going to use a string stream object to do that. Okay, so he goes into an infinite while loop. It's not really infinite because when you hit capital Q, he can exit. So he prints out a prompt message for you, which in this case, it's PGM greater than. Okay, so he prints out the prompt, and if you're looking at where the prompt is, it is part of the command line arguments. Right there. You can enter a prompt if you want. So the prompt comes from the command line arguments. The flush just makes sure that the prompt gets flushed out. Don't worry too much about it. Then you can see that he reads a line. And if he doesn't get it because end of file has been reached, he returns 0. So if you hit Control C, that causes an end of file character, and he will return. Otherwise, he gets a line, he reads it into line. He clears the vector because he doesn't want the contents of the previous line anymore, so he clears the vector. He clears the string stream right here. Then he stuffs the line into the string stream, and while there's more words in that string stream, he pushes them onto his string vector. When he's done, he has chopped that line up into words. Now he checks to see if the line was blank or if the line started with a comment, in which case he ignores it. Okay? But if not, you can see the ignore, he has nothing here. I know that looks funny, but that's fine. There's nothing in this if statement, right? It's an empty block, no worries. Else if, and now he's looking at each of the first word and checking to see what type of command it is. And now for each command, he knows how many arguments there should be. So at this point, he checks to make sure that you have given him the proper number of arguments. Okay, if you haven't, he throws an exception, saying the usage is and what the usage is. So he throws it out of here. Otherwise, he starts processing the command line arguments. In this case, it is to read a file name. And if you return false, he throws a string that says the read failed. If you return true, he's happy. Okay, moving down a little bit to his create, that required some integers. So in his create, the first and second arguments were, all three arguments actually are integers. So he again reuses his string stream by clearing it and stuffing in the different arguments. And as long as they succeed, he's happy. If not, he throws strings indicating what the problem was. At the end, he calls the create method with the arguments. If it succeeds, nothing happens. If it fails, he throws. Okay, down at the bottom, he catches. Down here, he catches. He really should have used a ampersand here to avoid copying the string. But you can see he prints the string, and then he doesn't actually exit the program. He just goes to the next line. So in this case, he recovers from the exception by continuing to the next line and reading it. Okay, and down here, if you enter Q, you can see he returns 0. Gets out of the infinite loop. Okay, so it's about a 114-line program. You can see that from down here. And it provides a nice testing framework that you can use when you're incrementally developing your program. Now, we give you these enormous PGM files. It's not a good idea to test using these big PGM files. Start small with like 1 by 1 PGM files, and then like 2 by 2, and then use rectangular ones. Don't just use square ones, use rectangular ones, but use small ones where you control what's going on. Okay, really the grade script should only be used after you've done thorough testing, because the grade scripts often use big files, and it's very hard to debug with big PGM files. You want to debug with small PGM files, which you can create. Okay? So that's what's going on with his testing programs. As I said, it's always a good idea to write them. They tend to be very much like what he has done here, which are they just take a bunch of commands. They call the different functions in your program, and they print out optionally debug information. Here he's not printing out debug information for you, but he certainly could have. Okay? So I know we've covered a lot. Okay, actually running out of juice here, so I am going to tell you that you should go and make sure that you review in his lecture notes at the very end the takeaways, because I've gone through all of these main points. Now I'm going to lose power, so I'm not going to, I'm going to at this point, I'm at 2%, so I'm still going to